Hey everybody, welcome back to the channel. Today we're going to start a new group of videos on what we affectionately call the dynamic Earth as we teach it. This video is going to be on Earth's interior, but we're going to have following videos on earthquakes, volcanism, and plate tectonics. Once we have them all out, we'll organize it into a playlist that you'll be able to watch. Once those are all out, there will be a card somewhere in this region so that you can access that playlist and follow all the material when you need to. This particular video is going to involve Earth's interior. We're going to talk about why we know what's going on inside, how we learned about the different layers, what those layers are, what constitutes them, the different characteristics, things like pressure and temperature, and all those things that are involved. We're going to talk about Earth's magnetic field and how the inside of the Earth helps to generate that. And just we're going to give you lots of visuals so that it's easy for you to follow. All right? So with that being said, we're going to go on to the video. Feel free to share this video with anybody that you think might benefit from it. Like and subscribe. I know everybody says that. And any teachers or educators out there, if you want to access any of our content, it's available in our Teachers Pay Teachers website, which will be in the bio down below. Otherwise, let's go and learn. See you.
So what we're going to be talking about, like I said in the intro, was Earth's interior. We're going to talk about what those layers are that are inside the Earth that you have learned about before in various other classes, but we're going to do them in a little bit more detail and connect them to the geology stuff that we have been doing in the previous units. So when we look at the inside of the Earth, we have to understand that the Earth's interior is varied. It's different. It's made up of multiple layers, all of which have different compositions and characteristics. So what do we mean by composition and characteristics? What we're talking about is basically that the inside of the Earth is different in terms of what it is physically made of, what are the minerals that we find in the different layers as we work our way down and down and down, thousands and thousands of kilometers, working our way towards the center. And it's different in terms of its physical characteristics, such as temperature, pressure. Okay, those are going to be critically important to differentiating the different zones that we are going to talk about. Now, you've heard about these before. We have the crust of the Earth, the mantle of the Earth, and the core of the Earth. Now, these layers are primarily made up of silicate materials at shallow levels. So when you're closer to the surface where we live, you're going to have a lot of silicates in those particular layers. As you work your way deeper and deeper and deeper and deeper down, your layers tend to become much more metallic and less silicates until we get to the center of the Earth, which is purely metal, almost all iron and nickel. Okay, now if we look at the Earth kind of looks like a Russian nesting doll. Okay, here we have a really great image where it's kind of showing the different layers separating out. Okay, cutting open like this. You have that center core, very, very hot. You have a layer around it that's called the outer core. The inner core is the glowy layer on the inside. You have the hot, rocky mantle, which is broken up into a lower mantle and an upper mantle. And you have the thin little layer on the outside, which is the crust, which is where we live and where most of the features that we see in every single daily life have occurred, and that you see mountains and valleys and rivers and the erosion and the weathering and all the other stuff that we've been talking about. So you can see that quite well in this image that you're looking at now. Now, like we said, as you go through the Earth, not only does the physical composition of the layers change, but the characteristics, the physical characteristics also change. In particular, when we're talking about this, you're going to be talking about three things: density, temperature, and pressure. As you descend, all three of them increase, but not always at the rate that we would assume. When we first were attempting to figure out what was going on the inside of the Earth, we came up with certain predictive ideas as to how the pressure would change, how the temperature would change, how the density would change. As we've done scientific experiments and actually researched the interior of the Earth, what we found is that sometimes we overestimated or undervalued or underestimated particular changes, or we saw trends where there weren't trends, or we just made mistakes. And that's what science is. Science is, here's an idea, let's test it, and if we find things that are incorrect, let us correct our original idea to reflect the actual data that we have collected, not just what we thought was true, but we actually are going to correct ourselves so that we can actually follow through on what the data is actually showing us. And so when you look at this chart right here, given to us by the state of New York. Wonderful chart. Okay, it's not color coded in the state of New York reference tables, but it's color coded here. What you can basically see is out here, you're going to have your crust, which is this thin little layer out here. Okay, incredibly useful chart. Okay, and then you have your upper plastic mantle here, your stiffer mantle here, your outer core, and then your inner core right here. Okay, on this side, you actually can see the density of the different layers, one of the important physical characteristics that we talked about. And so you see how the continental crust or the oceanic crust, depending on which one we're talking about, is either 2.7 or 3.0. We will get to that in a little while. Okay, we have the stiffer mantle right here, which has a density of between 3.3 and about 5.5 grams per cubic centimeter. You have the outer core, which is about 9.9 to about 12.1, and then you have the inner core, which is about 12.7 to about 13 grams per cubic centimeter. So you can definitely see a trend as you go deeper and deeper and deeper, your density does go up, and that makes sense with what we had said before. As your composition changes, you're going to go from silicates to more metallic, and so you're going to tend to have a higher density. Okay, this chart is also really useful. Once again, down here, if you look on the x-axis, you can see that it has the depth as you work your way down towards the center of the Earth in kilometers. Okay, and you have a temperature gauge here and a pressure gauge right here. Okay, and what we see right here is that as we work our way through the layers of the Earth, you can see that the temperature definitely does increase. Okay, but something strange happens where we get these weird partial meltings of things, or where we believe certain materials should be melting, but they're not actually melting. Okay, and that was something strange that we discovered as we studied the interior of the Earth. And what we realized is that the melting point also has to do a lot with the particular pressures that you're dealing with. Now, if you look at the chart up here, once again, you'll see that as you go deeper and deeper and deeper, the pressure increases. Okay, but it's not a perfectly straight, stiff, constant slope like you would expect. You do see that there is a curvature to it, and that was an interesting fact that we found as well. But once again, you can see that there is a increase in all these values as we go deeper and deeper and deeper, but it's not a straight linear line like, or linear relationship like we would have believed it was going to be. Now that we've talked about the physical characteristics and the chemical composition of the different layers of the Earth's interior, we're going to focus on the particular layers that exist there. Now, you've talked about this in classes before. I'm going to give you a little bit more information, maybe a little bit more in detail, connected to some of the geology stuff that we have done in the past, so that it should make a little bit more sense and how you can see how all of this does connect. This will also let you make connections through any charts or diagrams that you may be given access to in your class. So the first layer of the Earth that we're going to talk about is the crust. A lot of times the way people want to describe this is think of the crust like this, skin of the apple. It's the part of the apple that we see when we look at the apple, but it's not most of the apple. It's this thin outer coating, but a lot goes on out there. Okay, this is where the biosphere exists. This is where you have plate tectonics. This is where you have earthquakes. This is where you have volcanism. So it's very, very important that we understand what's going on here. Now, when geologists talk about a crust, they usually will break it up into two distinct types of crust. We have what we call the continental crust, and we have what we call the oceanic crust. Continental crust would be the part that underrides most of the continents, you know, North America, South America, Europe, and things like that. The oceanic crust would primarily be the seafloor. This is not to say that you can only find these types of crust in those particular places. There are plenty of places on the continents where the oceanic crust is visible. If you go to the Himalayas, for example, that is mostly oceanic crust that's been thrust up into the air 6.5 miles in some places. Why? Because when you get plate tectonics, when you get convergent boundaries, this crust can get pushed up. So don't always think that you can only find these types of crust in the particular places that they're named after. That's just the primary locations of formation and location. Okay? Typically, when geologists want to talk about these things, what they'll typically do is they'll refer to the crust as either being granitic or basaltic. The crust that tends to underlie, be the basement rock for the continent is granitic. There are obviously places where it's not just granite. And the ocean crust tends to be basaltic. Once again, there are places where it's not just basalt. It might be something like gabbro or some other particular type of rock. Now, the biggest thing between granite and basalt that makes them important is the density differences. Okay? Continental crust tends to have a density of about 2.72, and basaltic crust tends to be about like 2.9 to 3. Now that's a dramatic difference in terms of density, and that is definitely going to have a huge effect on what happens when these two types of crusts come into contact with each other. Okay, and this is going to lead to a lot of the things that we're going to see later on when we get to things like plate tectonics with subduction zones and things like that, and why particular slabs go underneath other slabs and things like that. Okay, when we look at these two types of crust, you're going to notice obviously visibly that there's a difference. When you're talking about continental crust, you're going to tend to be talking about stuff that's much lighter in color. Okay, you see it also tends to be much thicker. Oceanic crust tends to be much darker in color and tends to be much thinner in terms of how thick it particularly is. So when you're looking at the continents are going to be made up of rocks like you see right here, making it out of Half Dome in Yosemite National Park, big slabs of granite, and your basaltic oceanic crust is going to be that ugly black rock that you've seen 14 million times in lab at this point. Okay. Once again, not always. You can have oceanic crust that's stuff like gabbro and stuff like that. Another big difference that you're going to get, like you saw in the image, but here we have some actual values for you, is the thickness of the different types of crust. Okay, when we talk about continental crust averages 35, 40 kilometers, but there are places where it is up to 70 kilometers thick when you're talking underneath like the largest mountain ranges and stuff like that. And oceanic crust you see is much, much thinner. You're only talking 7 to 10 kilometers thick. There are places where it's only like 2 kilometers thick. Okay, and once again, you can see that there is a dramatic difference between the densities of 2.7 and 2.9 grams per cubic centimeter. And this is much lighter than the density of the mantle, which is about 3.3. Effectively, what this does is it causes the crust almost to act like a raft sitting on top of water. And you have that floating effect that you kind of get if you made a little wooden boat and put it on top of a container of water, and you would get it floating on top of there. You can almost think of the crust as like floating on top of the mantle. Not that the mantle is liquid, but the mantle has a much higher density than the crust above it, and so that's why you get this kind of like raft-like effect of all the plates, which is one of the things that's going to allow for like plate tectonics and movement like that. The next layer that we're going to talk about is going to be the Earth's mantle. Okay, now the Earth's mantle is one of these layers that we think of, oh, well, the inside of the Earth is just liquid magma and it's floating around. It's not exactly what it is. It is a very unique, very different structure from what most people consider it to be. And in fact, what we tend to do is we tend to split the mantle into two parts. So we have the upper mantle, which is semi-molten and displays plasticity. That's a fancy way of saying that this layer has the ability to kind of change and deform its shape with under extreme pressure. Okay, you will get some fracture, but it will, tend to flow a little bit more. And then you have the lower mantle, which is much more solid, or is usually referred to as the stiffer portion of the mantle. There's also a dramatic difference in terms of thickness between these two layers, which you'll see in an image in a minute or so. Now, both of these mantles primarily are made up of the minerals olivine and periodotite. Okay, we do see this, and we have discovered this because we have discovered some volcanism that does directly come from these places and has carried up these materials from the mantle, and so that allows us to understand what the mantle is made up of because that material has been brought up through various volcanic activities. Now, the mantle is incredibly important because the mantle is the site of convection cells. If you did your energy section already, you should understand that one of the ways that we can transfer energy is through this creation of convection cells, and convection cells being areas of differences in density, which causes particular fluids meaning gases or liquids or semi-molten solids, to move. And so what you create is these big loops of material rising that has a lower density and material sinking that has a higher density, and then the energy causes it to continuously create these big circles of material just rising and sinking and rising and sinking, and we'll see that in a second. So this is a sample of olivine that was collected from a volcanic opening, okay, and you can see the crystals right here, okay, this deep green color, which is what gives you the name olivine. Okay, in the image that you're going to look at now, here we have what we're talking about with the mantle. So your crust is this thin little layer up here. Okay, you have the upper mantle here, which is about a little less than 700 kilometers thick. Your lower mantle, which is almost 3,000 kilometers thick. So there's a marked difference. Your upper mantle here is the one that's going to display the plasticity, and this is going to be your lower, stiffer mantle right here. Okay. What we have found is that quite often you are going to get these plumes of material, this hot material that rises through the mantle, okay, and that is one of the things that we think of as the cause of large amounts of igneous activity, volcanic activity that we're going to have, whether that be plutonic material that cools beneath the Earth's surface and then gets uplifted, or whether that be stuff that is going to directly come out, okay, and become extrusive activity, such as the volcano that you see in this image or you've seen in the background of most of this slideshow. Okay, and obviously the closer you get to the core, the hotter and hotter it's going to get. We're going to talk about the interface between the core and the mantle in a little bit. Okay, now we were talking about those convection cells. So convection cells inside the Earth are going to be these large masses of rock or magma which move due to differences in temperature. So when it's super hot, it's going to tend to rise up, and as it cools down, when it gets to the top and it loses some of its heat to the crust, it's going to tend to sink down. Now, you're going to get these big loops that occur. These are enormous. Sometimes these can cover hundreds of square kilometers. Okay, so you're talking these are going to be underneath, whole continents, whole plates, large areas. But we think that these might be the driving forces behind a lot of the plate tectonics that we have. Okay, so you see here, as you have the hot material that's going to rise, when it interfaces with the core down here, it's going to rise up. Okay, it may hit a rift valley or ridge crest, and some of it may come out. As that happens, it's going to push these slabs away from each other. The further away it gets from this area, the cooler it's going to get. Eventually it gets to the point where it's very cold, it starts to sink back down. It comes in contact with that boundary again, warms up, and so this process is just going to happen over and over and over again. This is going to create what we call a convection current. Okay? And so what you can see in the two images that you have right here is basically that process happening. As it comes in contact with the core down here, it heats up that material rises up. Okay, and as it rises up, some of it may escape through mid-ocean ridges or rifts or rift valleys, and then it proceeds to pull the plate apart here and cool off and then sink back down. It's an absolutely wonderful image. If you want to pause it and screenshot it so you can include it in your notes or take a picture of it, this would be a really good image to include in your notes, and you could even label it with the different parts of rising material, slab pull, and cooling material here. Now, finally, we're going to get to the core, the inside of the Earth. Okay, the core of the Earth is primarily made out of nickel and iron. Those would be the chemical abbreviations for nickel and iron. I know iron is Fey. You'll learn about that in chemistry. Okay, it's an old Latin term, ferrous. Okay, now when we talk about the core is actually made up of two distinct parts. We have the outer core of the Earth, which is liquid iron and nickel, and we have the inner core of the Earth, which is a solid ball of iron and nickel. Okay, and in fact, the inner core of the Earth is so hot that it's actually hotter than the surface of the sun. So the inside of our Earth is actually hotter than the surface of the sun. Much smaller, but also hotter. And so when we look at your typical, image like we had at the beginning here you have your different layers. There's your thin little crust. There's your thicker mantle. This would be your outer core, and this glowing ball right here would be your inner core right there. So you kind of have that Russian nesting doll sort of image here. Now, one of the cool things that we've discovered is that the outer core and the inner core actually interact with each other. And one of the ideas that we have is that the inner core might revitalize itself over time, because what actually happens is this new idea that we have that's called the translation of the inner core. And what basically happens is part of the inner core slowly melts as it gets hotter and hotter and hotter and hotter and hotter. And as it gets hotter, okay, that material that's in the inner core is going to enrich certain mantle plumes and things like that with certain lighter elements. Okay, some of just the outer core's liquid dense layer is going to be, the iron and nickel is going to come from the melting of the inner core. But as that happens, you're also getting solidification and the crystallization of iron to add to the core. So basically it's recycling material from here to here and here outward. Okay, and this might also help some of those mantle plumes that are escaping outwards here to have more minerals coming up from the core. So this is a newer idea as to how and what is going on inside our core in a daily basis. Now, the Earth's core is awesome. It's cool. The fact that it's a big iron nickel ball at the center of the Earth is cool, and that it now does this translation thing. If you look up videos, they talk about how in the inside there may be mountains of iron. It's an amazing thing. There's a ton of information that we could get into a ton of depth with, but we're just trying to work our way through what you are responsible for in class. But feel free to look up any of that stuff if you want to. But the Earth's core, in fact, the fact that we have both a liquid outer core and a solid inner core are incredibly important for us here on the surface. And the reason why is because the Earth's core helps to generate what we call the Earth's magnetic field. Okay? And this magnetic field is super important because what the Earth's magnetic field does is it helps protect us from a lot of the cosmic radiation that's produced by stars and the sun and things like that. Now, the question is, how does it do this? Well, it does this relatively simply but beautifully. As the Earth rotates, as we spin, okay, the liquid outer core spins and sloshes around the solid inner core. And this creates something that physicists refer to as the dynamo effect. And they've actually recreated this in various labs where they take a big ball of iron or a big ball of aluminum and they surround it with liquid aluminum and they rotate it around. And as they do this, they generate a powerful electromagnet, okay? And that is exactly what's going on inside of our own planet. As our planet is spinning at about 15 degrees per hour, okay, that outer core moves around the inner core, and this is going to generate an incredible, powerful magnetic effect. Okay, and this was discovered by a variety of scientists out there. Faraday was one of the first people to understand how magnetism worked. Neil deGrasse Tyson has an absolutely wonderful video where he explains this. If I can find it, I will put a card on this slide where you can go see his speech where he talks about this during one of his interviews on Star Talk, but it's actually really well done. He does a much better job than I ever could. But basically what happens is, as that outer core is sloshing around the inner core, it's going to generate this magnetic field. And this magnetic field, the energy is going to get pushed out of the poles of the Earth, okay, as you see in the image here, and it's going to generate this magnetic field around the Earth. And anything that is electrical in nature can interact with this field and can get pulled in towards either the North Pole or the South Pole. Remember, we talked about this with auroras earlier in the year. That's what causes the northern lights and the southern lights. Now, why is this important to us in terms of life? Well, as we have a magnetic field, the sun in particular, but almost all stars, okay, are going to be producing highly charged energetic particles. Those energetic particles are going to try to hit the Earth. When they try to hit the Earth, what they would do, given enough time, is they slowly would chip away and eat away at our atmosphere. Okay? That would be bad for us. In fact, we think that this is what happened on Mars. Mars doesn't have a magnetic field, and we think this is what happened to it. As it stripped away the atmosphere, the planet got very, very cold. It lost the liquid water. All that water froze, and Mars is now a cold, dead world. Our planet has this active magnetic field around it, and so since it has this active magnetic field around it, this magnetic field can catch those high energy particles that are coming out, collect them at places like the poles or the Arctic or Antarctic regions, right? And it can generate auroras, which we view as these beautiful things, but which protects us from most of those dangerous particles. Now, this causes Earth's magnetic field to be a little bit uneven. The side facing the Earth tends to be much more compressed, and so what you'll tend to get is these smaller loops, and the side facing away from the sun tends to extend far out on the backside of the Earth. But this is incredibly important when you think about the fact that something 6,000 plus kilometers down inside of our Earth is protecting us from something that's, 92 million miles away or 150 million kilometers away from us in space. That interaction between the terrestrial and the astronomical is phenomenal in my opinion. And so it's really important to understand that this is going on and that this is super important. All right, so that takes care of the Earth's interior. I hope you found this interesting. I hope you found this educational. And like we said at the beginning, if you like this video, please like and subscribe. and we'll see you coming up in the next video where we'll be talking about something earth-shaking. I'm sorry, bad science teacher puns. Next video is on earthquakes. Alright, see you guys later. Bye.